Hello everybody, my name is Stephen Haas, and this is our crash course for our final exam in the Introduction into Statistics course. This course is going to cover statistics and also some probability and some similar areas on a fairly basic level. Things will get a little bit mathematical as we move along, but we're going to try to make it as painless as possible for you. Obviously, we hope that you've taken the time to read and do the other assignments, read the textbook, take advantage of whatever other resources we can provide to you. But the idea here is to try to do as much as possible to prepare you for the final exam and to kind of give you a comprehensive review of this course. We're going to be dealing primarily with numbers and formulas. We're going to be dealing a little bit with probability, but at the outset I'm going to introduce you to two dichotomies over here. And the first is the parameter versus the statistic. Both the parameter and the statistic are values that you derive from somewhere. You can measure them, and they help you gather information, of course. Or really, they are information that you gather, and they help you draw conclusions. The difference is that a parameter is a numerical value that's equivalent to an entire population, whereas a statistic is only a representative sample of an entire population. For example, if you are a doctor that is examining people for strep throat, and you examine 10 people and 2 of them have strep throat, well, that's a parameter because that's the entire group of people that you have sampled. That is your entire sample size. Whereas a statistic is something that is only representative. For example, if you're trying to determine what percentage of people with sore throats have strep, and you say, well, I've examined 20 people and about 10 of them have had strep, therefore I'm going to infer that the population as a whole, about half the people that have sore throats have strep. That would be a statistic. In other words, a statistic is only a component of the entire population. Our course, as you notice, it's called statistics, and because we are going to be dealing with situations in which you don't have all of the numbers, if you have a parameter, you have every single number you're looking for, well then there's no real need to infer and use confidence intervals and deviations and things like that, because you have all of the data you need. So you don't really need to study anything, you don't need to infer anything, and you don't get to have all this fun. So a parameter is when you are sampling the entire data pool, whereas a statistic is when you are only sampling a portion of the data pool. To distinguish between whether something is a parameter or a statistic, ask yourself if you're looking at the entire population or only examining some people from the entire population. If you want to ask yourself what percentage of the people in your household eat vanilla ice cream, and assuming you have a relatively small household, if you have 4 or 5 people in the household, it's relatively easy to do a survey. You can ask every single person in your family, do you like vanilla ice cream? And you'd get a parameter because that's your entire data pool. On the other hand, if you want to know how many people in the world like vanilla ice cream, well, you're probably not going to be able to survey all 7 billion of them, and so therefore you take a representative sample. You can do a scientific study, you can do a statistical analysis, and you can do a survey and try to infer that, try to extrapolate that to the rest of the population. But the data that you do collect, the 100 random people that you do sample, is going to be a statistic because it is only a component of the entire population that you are trying to study. Another example, a doctor examined 5 people and concluded 3 of them had the flu. Well, that's a parameter because the entire data pool is just these 5 people. On the other hand, if you're talking about a large pool of people and you say 3 of every 5, 60% of them got the flu last year of all 1,000 people in this city, well, that's a statistic, again, because you don't know precisely the information that regards your entire data pool. You only know a small cross-section of it, and you're going to try to infer the rest. The other type of data that we are going to look at is the distinction between qualitative and quantitative data. Qualitative is a description of an object or characteristic. It cannot be measured. It cannot be broken down into science. She is a nice person. He is a lousy person. He is mean. These are all things that cannot be measured on a scale of 1 to 10, then is an example of something that is qualitative if you say Joe is tall and has light skin. There's no particular number you're assigning over here, and therefore you're talking about a qualitative judgment. On the other hand, if your determination is based and can be put into numbers, then it is considered quantitative. Instead of saying Joe has tall and has light skin, you can say Joe is 6'1" and his skin is in the 24th percentile of skin shade from lightest to darkest among Caucasian males. Sounds like a little bit of a silly statistic, but it is a quantitative statistic, and we are going to be dealing in this course exclusively with quantitative statistics. We're not going to be making value judgments on things. We are going to be determining what regards things in terms of numbers and only things that can be measured in numbers. If you want to look at qualitative data, take sociology. If you're taking statistics, you are looking at quantitative data. The next issue I want to discuss is how data is plotted and put on charts and graphs. We're not going to spend too much time on this, although this is relatively simple stuff, but we'll still go through some of this stuff over here. If you have a bunch of data points, a bunch of numbers, you can make a chart or a graph to represent the distribution. Obviously, you have to be told the number of classes, in other words, the number of groups that you're referring to. Let's take a look at one example over here, and we'll look at this as it's established in a few different ways. Here you have a list of tests scored on an exam, 67, 78, all the way through 92 at the end over here, so you have a whole bunch of samples over here. And one way to put it is in a frequency chart. Now, a frequency, here you have the classes. The classes are, you can see there are 4 of them, 60 to 69, 70 to 79, 80 to 89, and 90 to 100. Those, of course, are relatively arbitrary. If you wanted to have classes be 60 to 64, and then 65 to 69, etc., all the way up to 100, then you would have more classes. Then you would have 8 classes. So it is relatively arbitrary how you pick your classes, but once you pick the classes, then determining how many in each class is easy. The frequency is how often each value appears within that class. In this series of grades, you have 4 60 to 69s, you have 9 70 to 79s, you have 7 80 to 89s, and of course 6 between 90 and 100. Cumulative frequency, another very important concept in statistics, is the total number of times, the total number of values you've had in that class and all classes below it. So for example, if we were starting from the low end, so you have 4 grades in the 60s, then you have 13 grades in the 60s and 70s. Really, that's just the frequency of each group underneath it combined. So if, for example, if you want to know how many students got below a 79, it would be 13 because that's a cumulative frequency. Of course, you could just count the numbers in the frequency because this chart is relatively simple, but if you have more complex chart, the cumulative frequency can help. Between the cumulative frequency of 80 to 89 is 20, because there are 4, 9, and 7, which equals 20 altogether. And then 26 if you include the 90 to 100, because there are 26 grades altogether. Notice the cumulative frequency of the highest group, of course, has to be the same number of total values you have altogether. If you can also draw it in what's sometimes referred to as a frequency polygon, or this kind of a chart, where you have the different values and you kind of illustrate the different classes as they relate to each other. In this case, the lowest value is 60 to 69, then you have the highest value up here at 9 in 70 to 79, then down to 7, 80 to 89, and down to 6 from 90 to 100. The 4 points that are plotted are the same 4 from the frequency column altogether. The axes are the class down here and the frequency up here. And drawing one of these should be relatively self-explanatory. What you need to do is you have to draw an axis. Draw one axis like this, draw another axis like that, put your classes down over here in this axis, put your frequency in this axis, and you don't have to make these up. You don't have to think of them yourselves. Just look at the chart. Whatever chart you're given, use the class on one axis, and use the frequency on the other. Now in this case the frequency goes up to 10, that's why I used the frequency that went up to 10. If the frequency went up to 20, obviously I'd have to use a different scale. Instead of saying 2, 4, 6, 8, 10, I might have said 4, 8, 12, 16, 20. Either way, that is how to draw a graph. There's another type of data distribution method called the histogram. Now this happens to be a different set of data. This is not the same chart, not based on the same chart over here. This one happened to be created with Excel, but creating it with a pencil and paper is also very easy. A histogram is a graphical representation of the distribution data, and you use the two variables as the axes. In this case, you have the number of students over here and the points over here. Notice in this graph we had the class and the frequency. In this chart we have the points and the students, but it's the same thing. The number of points is the class. Just like here the number of points were in the 60s, in the 70s, in the 80s, and from 90 to 100. In this diagram, in the histogram, the points are also the classes, from 0 to 10, all the way to 90 to 100. The other axis, the y-axis, the axis over here, in this diagram we called it the frequency, in this one we call it the number of students, but again it's the same thing. The number of students is the frequency. The frequency is how often something occurs. So in this diagram, for example, you can see from 0 to 10 points, you had about 8 students, it looks like. From 10 to 20, you have 10 students. From 20 to 30, it looks like you have about 23 students, give or take. 30 to 40, you have about 29 students. 40 to 50, you have about 35. 50 to 60, it tops out at over 50 students, and then it goes back down towards the end. Histograms are very easy to draw. Again, just take out a pen and paper and draw two axes. Put your classes down here and your frequency up here, however you want to describe them. Put your points or classes in terms of the numbers, and put your frequency over here, and just make little bars to represent how high each class goes. Histograms are useful because they give you kind of a pictorial look at the distribution of all the results. And a little bit later on, of course, distributions will become very important. Next, I want to move into probability for a little bit. Only two quick videos on probability. Probability is, of course, the study of the likelihood of something happening. If you flip a coin, you may intuitively realize that you have a 1 in 2 chance of getting heads and a 1 in 2 chance of getting tails. That is really probability at its most basic. Probability is the number of results in a given range divided by the number of possible results. For example, if you throw a die has 6 sides. What are your odds of rolling a 3? Well, the answer, of course, is 1 in 6, because there's only one 3, and there are 6 possibilities, so it's 1 in 6. What are your odds of rolling either a 2 or a 3? Well, there are 2 possibilities there, and there are 6 altogether. 2 possibilities that you're looking for, and 6 altogether, so your odds would be 2 out of 6. So just to take the graph we got before, just to make things a tiny little bit more complex, but really still relatively easy. This was the graph we saw before, the classes from 60s, 70s, 80s, and 90s, and we looked at the frequency. What is the probability of any given student in this class scoring a 70 to a 79? Well, there are 26 possibilities altogether. We know that either by adding up all the frequencies or by just looking at the cumulative frequency for the highest group. So there are 26 possibilities altogether. How many students got in the 70 to 79 range? Well, you can see there are 9 of them. So therefore, the probability of any one student at random getting in the 70s would be 9 out of 26. What's the probability of getting below 80? This is where the cumulative frequency comes in. Well, the cumulative frequency goes up to 79. That goes up to 79 is 13. So that means there are 13 students that got up to 80. And you also could have gotten that just by adding the frequency of the 60s and the 70s. Either way, you get 13 results that you're looking for. The total probability, the total number of results possible, are 26. So of course your probability of a student at random getting below 80 is 13 out of 26. What's the probability of a student getting above 70? Well, we have three groups that get above 70. The 70 to 79 group, the 80 to 89 group, and the 90 to 100 group. It's 9 plus 7, which is 16. 16 plus 6 is 22. So there are 22 students that got above 70. There are 26 possible results altogether. And so therefore the probability of any one student at random getting above a 70 would be 22 out of 26. Generally speaking, of course, whenever you're talking about probability, the lowest probability you can possibly have is 0. The highest probability you can possibly have is 1. A 1 means a certainty. For example, if I told you what are the odds of rolling a heads or a tails when you flip a coin, of flipping a heads or a tails when you flip a coin, the answer is 1. You have to flip either a heads or a tails. 1 means 100% possibility. So you can see all of these fractions are numbers between 0 and 1. It's not possible in a probability fraction for the numerator to be higher than the denominator. The highest you can possibly get is exactly 1. The lowest you can possibly get is exactly 0. What about probabilities of a series of results? You roll a die 3 times. What are your odds of getting 3 6s in a row? Well, in order to do that, in order to figure out the probability of consecutive results, you simply have to multiply all of the probabilities of all of the individual results together. So, for example, if I say, what are the odds of rolling 3 1s in a row? Well, let's see. The first die, what are the odds of getting a 1? 1 out of 6. The second die, what are the odds of getting a 1? 1 out of 6 again. The third die, what are the odds of getting another 1, are 1 out of 6 again. So you have to multiply each chance by each other. When you multiply 1 out of 6 times 1 out of 6 times 1 out of 6, the numerator is 1 times 1 times 1, which is 1. You multiply the denominators, which is 6 times 6 times 6, which is 216. So the odds of getting 3 1s in a row when you roll a die 3 times are only 1 out of 216. Just to give you another example that's maybe a little bit more complex, what if I have 2 dice and a coin, and I'm going to throw both dice, and then I'm going to flip the coin. I'm playing some kind of weird casino game. And so what are the odds of my getting snake eyes, which means 2 1s, a 1, and a heads? What are the odds of getting all 3 of those results? Well, let's take the probability of each one individually. What are the odds of getting a 1 when you roll a 6-sided die? 1 in 6. What are the odds of getting another 1 in 6? What are the odds of getting heads? Of course, there are 2 sides of a coin, so it's 1 in 2. So the odds of getting snake eyes and a heads would be 1 over 6 times 6, which is 36, times 2 is 72. What are the odds, on the other hand, of my getting, if I throw a die, and then I flip 3 coins, and I ask, what are my odds of getting an odd number, and then, of rolling an odd number, and then 3 straight tails? 3 straight tails. Well, okay, what are the odds of getting my odd number? Well, odd number, there are 3 possibilities. If you roll a die, there are 6 numbers, 1, 2, 3, 4, 5, 6. Of those, 3 of them are odd, 1, 3, and 5. So the odds of that are 3 and 6, which is the same thing as 1 and 2. And then multiplied by, well, 3 consecutive tails. What are the odds of getting 3 consecutive tails? Well, that's 1 and 2. Each tails is 1 and 2. So that's 1 and 2 times 1 and 2. And the answer to that is 1 over 2 to the 4, 2 times 2 times 2 times 2, which is 16. So let's take a look at something slightly more complicated. Probability of any individual 7-digit phone number being 3526505. Again, I just picked that out of the blue. What are the odds of a particular 7-digit phone number being this number? 3526505, a random number that I pick in the phone book. Assuming they all have the same chances, each number can be each other. Each digit can be each number. Well, how would you figure that out? Each digit, let's say the first digit, what are the odds of it being a 3? 1 in 10, because a 3 is one number out of 10 possible numbers. Same thing with all the rest of the numbers, the 5, the 2, the 6, the 5, the 0, the 5. So each digit is 1 in 10, so it's really 1 in 10 times 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 1 in 10, because there are 7 numbers. So it's 1 over 10 to the 7th power, in other words, times itself 7 times, and if you just multiply that out 7 times, it would be 1 in 10 million. What if you put some conditions on it? Then you have to watch out for those conditions. So let's say, for example, you have the same rules as above, but this time we know the last digit cannot be a 7, 8, or 9. We know the first 6 digits can be anything, and the last digit cannot be 7, 8, or 9. So how many different possibilities are there? Well, the first 6 digits stay as 1 in 10, 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 but the last digit, now there's only 7 possibilities. This last digit can only be a 0, 1, 2, 3, 4, 5, or 6. So for there's only 7 possibilities. So instead of being 1 over 10 to the 7th power, it would be 1 over 10 times 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 1 over 7. Because that last one, there's only 7 possibilities, and if you multiply those up, you're going to get 7 million instead of 10 million. So always make sure to account for the conditions. Take the odds of each thing individually, take the odds of each possibility individually, multiply them all up. Obviously, you can do this on a calculator, you don't have to do it by hand, and getting the probability of any given series of results should be relatively easy. Other things, for example, you might be asked something like, what are the odds of rolling doubles on a particular die? Well, doubles is a little bit harder than saying a 1 and a 1. The odds of rolling a 1 and a 1 are 1 over 6 times 1 over 6, but the odds of rolling doubles, the first number could be anything. The first number could be a 1, 2, 3, 4, 5, or 6, and you could still roll doubles by rolling the same number again. So if you think about it, the odds of rolling doubles, whenever you throw 2 dice, when you're playing Monopoly or whatever it is, whenever you roll 2 dice, the odds of rolling doubles are 1 in 6. Because the first one could be anything, then the second one has to be the same as the first one. So if you roll a 4, then you have a 1 in 6 chance of rolling another 4. If you roll a 2, you have a 1 in 6 chance of rolling another 2, etc. So, for example, if you were playing a game and you had to put money in order to roll, and you won a certain amount of money for hitting a double, it would really, in order to be a fair game, it would have to be 6 times the amount. If you put in $100 and won $600 if you hit doubles, that would be a fair game. If you'd get $700 if you hit doubles, well, that's a really good game that you should play because you're getting good odds. You're getting better. You're taking a 1 in 6 chance, but you're going to win 7 times your investment. On the other hand, if you're only going to get 500 if you hit doubles, it's not a good bet because there you're taking a 1 in 6 chance to only win 5 times the amount. So those are some of the general issues regarding probability. Our next discussion regarding probability is the idea of the binomial experiment. Not all experiments are binomial, but binomial is a type of experiment that happens to be relatively easy to read and use from a statistical standpoint. For example, in questions regarding whether you're going to vote for a certain candidate, the idea is to put together a binomial experiment, which is a lot easier to analyze than other types of experiments. A binomial experiment means it has a fixed number of independent trials. For example, if you flip a coin 10 times in a row, that is a fixed number of independent trials. One result has nothing to do with any other result. Just because you roll 3 heads in a row does not mean you're any more likely to roll a heads or a tails on the 4th try. Anytime you have an experiment where all the trials, all the things that you're doing are independent of each other, that can be a binomial experiment, but it also has to have exactly two outcomes for each trial. For example, when you flip a coin, you can only have one of two possible outcomes, heads or tails, and so therefore it can be again a binomial experiment because each trial has exactly two outcomes. Now when you roll a die, and when you're looking to see which number you get, well then there are 6 possible outcomes. You can either get a 1, 2, 3, 4, 5, or 6. That wouldn't be a binomial experiment. However, if the results you're looking for can be classified as one of two categories, well then it can be a binomial experiment. For example, if you say, I'm going to roll a die 5 times, and I'm going to see how many 3s I get. Well, that could be a binomial experiment. You have a fixed number of independent trials, and also what you're looking for is either yes, a 3, or not a 3. Now, of course, they're not equal in terms of chance. There's 5 times as good a chance that you're not going to get a 3 as that you are going to get a 3. But still, in terms of your experiment, there are only 2 possible results, a 3 and not a 3. So that could still be a binomial experiment. The probability that each outcome in a binomial experiment remains the same for each trial. In other words, one trial, one experiment, one part of the experiment does not impact any of the others. Some examples of a binomial experiment: flip a coin 30 times and see how many heads you get. The number of trials is fixed because you have 30. Each trial is independent of the other. Again, just because you flip a heads first doesn't mean you're any more likely to flip a heads second or a tails second. And there is a precise number of there's a precise number of trials there, and there are exactly 2 outcomes to each trial. I just changed the middle clause over here, which was a mistake. But in this case, there are 2 possible outcomes, heads and tails. Therefore, it's a binomial experiment. What about this? Sandra rolled a 6-sided number cube, in other words, a die, until a 3 appeared. Well, why is this not a binomial experiment? Now, of course, each roll is either going to get a 3 or not a 3, but the number of trials is not fixed. Maybe she'll roll a 3 on the first time, maybe it'll take until the 10th time. Because the number of experiments, the number of trials is not fixed from the outset, it is not considered a binomial experiment. But as I mentioned before, it can be used even when there are 2 or more possible results, when there are more than 2 possible results, such as in the case of rolling a die, as long as the probabilities are either A or not A. For example, if you have a trial and you have the probability of A happening, whatever A happens to be, is 30%, 0.3. The probability of B happening is 60%, or 0.6. And the probability of C happening is 10%, and there are 50 trials. You can still do it, even though there are 3 different possible results, you can still have a binomial experiment to consider the chances of A or not A. If you're looking for which is going to happen, A, B, or C, that's not a binomial experiment because there are 3 possibilities. However, if you're looking for an experiment to determine is an A going to come up or is not A going to come up, or is a B going to come up or is not B going to come up, those could be considered, or those would be considered, a binomial experiment as long as you have a fixed number of trials and as long as the tests are independent from each other. Some examples based on these numbers over here. Well, if you roll each individual time, the probability of not A is 70%. Why? Because the probability of A, of course, is 30%, and the other 2 combined are 70. Probability of B would be 60, and therefore the probability of not B is 40. And the probability of not C, of course, is 90% because the probability of C is 10%. Now, one thing you might have noticed, but it's also important to remember, is that in any binomial experiment, the probability of both results combined when added together have to, of course, equal 1. 70% plus 30% equals, of course, 100%, which is the same as 1. 40% plus 60%, again, of course, is 1, and 90% plus 10%. Of course, equals 1. Our next section is about averages and standard deviations. Average is a relatively simple concept that you probably know a little bit about. Averages are simply the middle value. Well, really, there are 3 types of averages. One of them that's going to be very important to this course, and the other that are pretty irrelevant to this course. The first one is the median. That's the middle value. For example, if you have a 90, 85, and an 80, well, then the median is the middle. If you have a 90, 89, and 80, well, the 89 is the middle. Whatever the value, you just line up all the values, take the one in the middle, that's the median. If there are two in the middle, in other words, you have an even number of values, then you just take the average of the two in the middle. That's relatively simple. We're really not going to focus on that in this course. We're also not going to focus on the mode. The mode is the one that occurs the most often. If you have a 90, a 90, and an 80, and a 70, well, then the 90 is the mode. Again, not very important. What is critical to this course, and the thing that usually is used when you're talking about statistical analyses, is the mean. And in statistics, the mean is symbolized by this Greek letter. In Greek, I think this is the letter mu. We don't have a letter like that in English, but they had a letter like that in Greek, and so we're going to use that symbol for the rest of the course to mean the mean. And the mu, or the mean, is all of the results divided by however many samples you have. So to give you a quick example, if you have test scores of 71, 77, 82, 85, 89, 93, and 93, well, in the median, just pick the one in the middle. There are 7 altogether, so the fourth one, the one in the middle, is the 85. The mode is the 93, but what is critical, and what's important, is the mean. How do you get the mean? Well, let's put a calculator up here. Again, it should be relatively easy to do, but we will do it. 71 plus 77 plus 82 plus 85 plus 89 plus 93 plus 93 is 590. Divide that by your sample size, which is 7, and you have 84.285. I rounded it off to 84.29. That is the mean, and the mean is by far the most important one when it comes to calculating statistics. That doesn't mean that it's always the best determiner. Sometimes, for example, the median means more. If you're looking at the median income for a city, then the average income for a city, the median, namely the middle person, might actually have more significance than the mean. The mean can be skewed by a really high result. For example, if you added a test score over here, instead of making this a 71, you made this a 0, well, that wouldn't change the median, but it would change the mean dramatically, because the mean would go much lower. Now, if you're looking for the average among all these people, let's say, for example, test scores, you can make an argument that the median is just as good a monitor. But when you're talking about statistics, when you're talking about the other things that we're going to learn in this course, the mean is by far the most used quantity. And the first application of the mean we are going to look at is the standard deviation. Standard deviation in statistics is represented by the Greek letter sigma, which is over here. And standard deviation is a measure by which you determine how far the averages are off from the mean, how different they are from the mean. Just to give you an example of where standard deviation would be important, let's say we had 3 test scores, or we had 2 tests. One had 3 scores, 80, 85, and 90. The other also had 3 test scores, 70, 85, and 100. Now, these numbers are actually going to have the same, both tests are going to have the same mean. The mean is going to be 85. If you do 80 plus 85 plus 90, you're going to get 255, and divide by 3, the mean is going to be 255. And 255. I'm sorry, the mean is 85. And the mean for the bottom one is also going to be 85. The median is also going to be 85 for both. But you can see there's a fundamental difference between these 2 tests. Whereas the top one, the scores were relatively close to each other, on the bottom one, the scores were very disparate from each other. Very often when you're talking about how good a particular test is, it doesn't have to be a numerical test, it could be any kind of a test, something that has a low standard deviation, in other words where the results are bunched towards the middle, usually has a higher scientific validity than tests where there are just wild results all over the place. So let's look at standard deviation and how to calculate it. And as we discussed a moment ago, standard deviation shows how much variation or dispersion there is from the average. And in this case, when we say average, we mean the mean. Low standard deviation means the data points tend to be very close to the middle, whereas a high standard deviation indicates the data points are spread out over a large range of values. For example, if all of your values are the same, if you take 5 tests and you get 80, 80, 80, 80, 80, and 80, well, then the standard deviation will be 0. The further apart they are from the mean, the higher the standard deviation will be. How do you calculate standard deviation? Well, it's a fairly complex formula, and I'm going to show it to you over here. You don't necessarily have to, actually you probably should remember how to do it, but you can do it on Excel also, as I'll show you how to do in a few moments. But if you look, for example, standard deviation, you have to square each value's distance from the mean and add them together, and divide the number by the sample size minus 1. And you have to take the square root of the result. So it's a fairly complex formula, and I'm going to show you how to do it by hand, and then I'm going to show you how to do it in Excel. So again, this means, let's take an example here. We've got 10 during the last 10 games, Team A scored the following number of goals: 0, 1, 1, 2, 3, 3, 4, 4, 5, and 7. First thing you have to do is calculate the mean, which is the average, because you can't tell the difference. Remember, the first step is to square each value's distance or difference from the mean. Take multiply that by itself. And but in order to figure out the difference from the mean, you have to figure out the mean. So you got to add them together and divide by the number of samples. If you add all these numbers together, you get 30, and there are 10 samples altogether. 30 divided by 10 is 3. So there are the mean, the average, is 3. The distances from the mean for each of these are, well, 0 is how many away from 3? 3. 1 is how many away from 3? 2. 1 again is 2 away. The 2 over here is 1 away from the mean. The 2 3s are, of course, 0 away from the mean because they are the mean. And the 4s, of course, are 1 away from the mean. And 5 is 2 away from the mean. And 7 is, of course, 4 away from the mean. Makes no difference which direction. Whether it's higher or lower doesn't really matter. In fact, when you square them, if you do it mathematically and you square it, you'll see that whether you use the negative or positive, it makes no difference, because when you square something, you always get a positive result. If you square these, namely 3 squared is 9, 2 squared is 4, 2 squared is another 4, 1 squared is 1, 0 and 0 squared are 0 and 0, and then again 1, 1 squared, 2 squared, 4 squared. Altogether, you got a 9, 4, 4, 1, 0, 0, 1, 4, 16. Add them together. If you add all these together, again, you'll just have to take my word for it, it makes 40. Then you divide it by the number of samples divided by, minus 1. You've got 10 samples, so you subtract 1, you have 9, and your standard deviation is 40 divided by 9, which is 4.44, and that means, and you take the square root of that, and get that you would have to use a calculator for, and the answer is 2.108. If we wanted to see how to do this the long way would be to say the square root of the standard deviation, namely the sigma, is the square root of all of the differences from the mean. And what's the first difference from the mean was 3 squared plus 1 squared, etc., 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 plus 2 squared plus 1 squared plus etc. In other words, all of the distances from the mean squared. I'll just make an ellipse over here, divided by n minus 1. Whenever we talk about n in this course, we're talking about the number of the sample size. So it'll be 3 squared plus 2 squared plus 2 squared plus 1 squared plus 0 squared plus 1 squared plus 1 squared plus 2 squared plus 4 squared. You can then do it on a calculator, and the answer would come out to 40 altogether. Divide by 9, which is 4.44, and take the take the square root of that. If you're using Excel, if you happen to use Excel, or really any spreadsheet program, if you want to find out the mean, by the way, you can use the average function. You can just type equals average, and let me put the top over here so you can see the formula bar. It's the average of, and just put a parentheses and put all the numbers you're talking about over here. Press the tab key, and you can see it's 3.1. I guess I must have mistyped something. Of course I did. I put an extra 4 here, so that's a mistake. I'm just going to copy and paste. I put 3 4s when in fact there should really only have been 2 4s. So I'm going to correct that. Yeah, and then our average turns into 3. If you want the standard deviation, well, Excel allows you to do that simply by pressing STDEV, standard deviation. And we're going to highlight all of these, press the tab key, and the standard deviation comes out. Excuse me, I just made another mistake. I had left out a 3. But anyway, these were the 10. I'll do it again just to make sure that you believe me. These were the 10 that we originally had. 0, 1, 1, 2, 3, 3, 4, 5, 4, 4, 5, 7. So I'm going to go equals STDEV, open parentheses, put all of these in here, and your answer is 2.108185. And in our example, I rounded it off to 2.18. You can round it off to usually 2 spots. You want to do 3 spots, that's fine also. But either way, that's to figure out the valuation. Now, the standard deviation. That in and of itself doesn't mean anything. The fact that the standard deviation for this number of goals is 2.18, that in itself doesn't really have any significance. It does have significance when we're going to discuss a little bit later on in the course, really just in a few minutes as a matter of fact, the idea of distributions, and later on when we look at the idea of confidence intervals and comparing data sets. Now let's look at what's sometimes referred to as the normal distribution. Now the normal distribution is based on a very interesting fact about really the nature of the universe, and that is that almost no matter what the quantity, almost no matter what it is you're measured, if things are random, if you have a centralized mean, a centralized average that things are based on, whether it be a test that's being taken or elections that are being run, if the results are randomly distributed from some sort of middle, from some sort of mean, they tend to distribute in a very stark way. They tend to distribute in a way that we'll look at in a minute, but basically most of the results tend to be right around the middle, and they tend to fall off as they move away from the middle. We'll see how this looks in a minute. Sometimes also referred to as a bell curve. You might have heard that expression before. So the normal distribution is a very commonly occurring continuous probability distribution that tells you the probability of an observation in some context will fall between any two numbers, and it's useful because under normal conditions, the mean, namely the average of many random variables independently drawn from the same distribution, is distributed approximately consistently. Very, complex way of looking at it. You may not understand what that means in English, but hopefully this will help. What this means is that this is a standard deviation curve, a normal standard deviation curve that will apply in many different contexts. Pretty much whenever you have random results that are distributed around the mean, as you increase the sample size, as you try it more and more times again, your odds of getting a result look something like this. Obviously, the highest possibility of results, the highest number of results you're going to get, are the ones right at the mean. 0 means at the mean. As you get further and further away, as you get much higher than the mean, the odds get lower and lower. In other words, the most results you're going to get right at the mean. A little bit away from the mean, you're still going to get high results. As you get further and further away from the mean, the results go down and down to the point that when you're really far away from the mean, way over here and way over here, you are going to have very few results. These numbers over here, down here, these numbers from negative 0.5, positive 0.5 to 1, 2, 3, those are measured in standard deviations. Remember how we figured out the standard deviation, how you figure it out from any data set, from any population? You just square them all, add them together, divide by n-1, and take the square root of the whole thing? Well, what the normal distribution curve says is that if you figure out something standard deviation, a series of results. You have 1,000 results of an exam. You have 1,000 scores in a basketball game. Whatever. If you look at the mean and you figure out the standard deviation of all of them, there are going to be roughly, as you can see over here, if about 19.1% on either side within a half a standard deviation. Now 19 times 1 plus 19.1 plus 19.1 is 38.2, which means that 38.2% of all of your results will be approximately within a half a standard deviation in each direction. If you go to a full standard deviation in each direction, in other words from 0 to 1 and from 0 to -1, one full standard deviation above the mean and one full standard deviation below the mean, well now let's add up what you have in this whole area. You have the 38.2 that we just looked at, plus 15 plus 15, that's 68.2. So between -1 standard deviation away from the mean and +1 standard deviation away from the mean, you can expect about 68.2% of your results. So just to give you a wild example, if we determined that the average score, the mean score in a basketball game is 100 points for each team. If we decided the NBA basketball game has an average mean score of 100 points per team per game, and we wanted to figure out, okay, we figured out the standard deviation. In other words, we take all the games, we square them, we add up the squares, divide by n-1, take the square root, and we find out that a standard deviation is 5 points, let's say. I'm not saying it is, but let's just say we come out that the standard deviation in a basketball game is 5 points from the mean. So if we take one standard deviation above and one standard deviation below, in our case, that would be 95 to 105, because the standard deviation is 5 points, we would expect approximately 68.2% of all basketball games, in other words, each team scores, 68.2% of them would be between 95 and 105. Now, in real life, I think the standard deviation is probably bigger than that. I would guess the NBA standard deviation is probably closer to 10 points than 5 points. But for purposes of our hypothetical, if standard deviation is 5 points in an NBA game, then we would expect 68.2% of the time that the teams will score between 95 and 105. What if we spread it out to 2 standard deviations? Well, we had 68.2 in the middle. Now 9.2 plus 9.2 is 18.4, so 68.2 plus 18.4 is 86.6. And then we have the 4.4 on the outside. In other words, we've got 8.8 altogether more than that, and that comes out to over 95%. It comes out to 95.4%. So I'm just adding up all the numbers that come in these various ranges. From -2 standard deviations to +2 standard deviations, we have over 95% of the results in the normal curve. To get back to our basketball example, if the mean of an NBA team scoring is 100 points, and if the standard deviation is 5, so 2 standard deviations is 10, which means that between 90 and 110, that's 2 standard deviations in each direction, we would expect 95.4% of all scores to be in that range. Now, of course, that's not what happens, which is why I was thinking in my mind that the NBA standard deviation has got to be a lot more than that. But just for argument's sake, let's say the standard deviation was 10 points. If the standard deviation was 10 points and the mean was 100, then you would expect 95.4% of all teams scoring would be between 80 and 120, because that would be 2 standard deviations. Now, of course, this only applies when the distribution is random. Now, in a basketball league, the distribution might not be random. It might be affected by things like parity. If you have some really good teams and some really bad teams, well, then the distribution is going to be larger, and that's really going to manifest itself in higher standard deviations. If you have, let's say you have put a bunch of teams together that are roughly equal to each other, well, then the standard deviation of the scoring is going to be much closer because the games are going to be much closer. On the other hand, if you have teams that are much, much better than the other, then the standard deviation is going to be much higher. But for any data set, you can take a standard deviation, and under normal circumstances, you are going to have the standard deviation follow this sort of a curve. Now, what we have over here is what is sometimes referred to as the z-table. And for the rest of the course, whenever I refer to z means the probability content of a normal distribution. So let's look at how to read this chart. This means if, let's say, this is the number of standard deviations on the left side, and this is just a continuation of the number. So this is 0.00. This number would be 0.01. This number would be 0.02, because again, 0.0 and then the 2 at the end. Let's say this number over here would be 1.64. And this is a way to tell the probability of your number, whatever your number is, whatever number you're looking for, being within that number of standard deviations from the mean. So if I take any quantity, and it could be a test score, it could be a basketball score, it could be pretty much anything, and I figure out the standard deviation, which is always the first step. If you don't figure out the standard deviation, this entire thing is totally useless. And I say, what are the chances of this score being within 2.43 standard deviations of the mean, assuming a normal curve? Well, I go over here and look at 2.4, and then we said 2.43, so I'm going to do 2.43, which is in this column, and the answer is 0.9925, which is 99. Remember, the highest, of course, is 1, so it's 99.25%, which means any piece of data that you have, it's going to be that you put in a normal distribution curve, a normal randomly generated score. There's a 99.25% chance that it's going to be within 2.4 standard deviations of the mean. Just what we looked at a few moments ago, I told you that there's a 95.4 chance that it will be within 2 standard deviations, and lo and behold, well, the 2.0 standard deviations, it actually says 97.72%, but that's because this is counting the maximum. It's not counting both sides. You know, in this chart, when I said 2 standard deviations either way. When the distribution table says up to 2 standard deviations above, it's referring to everything to the left of this number over here. In other words, it's including all of this, including this area down here. It means up to 2 standard deviations above. Obviously, if you want to determine what are the odds of it being within 2 standard deviations either way, you have to take the lower number. You have to really double you have to take 1 minus double whatever this number would indicate. Again, I'm sorry, I'm not being very clear over here. But what this means is that there is a 97.72% chance that whatever your random data is going to be something less than 2 standard deviations above the mean. If you took it in both directions, now 1 minus 0.9772 is 0.0228. If we would double that and subtract that from 100, then we would get the odds of being within 2 standard deviations either way. This is the probability content from negative infinity, which means from the lowest number possible, whatever that might be, all the way up to this number of standard deviations. Now, if I ask you, for example, what are the odds of let's say, if I ask you how many standard deviations do I need in order to be 95% certain that my data will be less than that number of standard deviations away? Well, then I'd look for the 95. I'd look for the 95%. Now I'm scrolling over here. I see it's right in between here and here. This is 94.95. This is 95.05. So it would be right around 1.65. We'll call it 1.65 standard deviations. Now, whether you actually have to use the number on this chart, or whether you have to essentially have or double the Now that it's less than 1 really depends on the circumstances, and we're going to discuss when you have to do each one. It really depends on whether it's a two-tailed problem or a one-tailed problem, and we're going to get to that later on. But I just want to familiarize you with this chart. What this chart symbolizes is the probability, in other words, the chances that whatever your data is going to be within that number of standard deviations away from the mean. Notice, of course, 0 is already 0.5, and the reason is because it's going to be less than 0 is everything on this side of the chart. If this is the 0, if this chart tells you what are the odds of it being less than this number of standard deviations higher than the mean, so it means that this entire half of the chart, this entire left half of the chart over here, because all this stuff is less than 0. That's why it's 50%. As you go further up, the numbers get higher and higher and higher, all the way until 3 standard deviations, which is all the way on the bottom over here, which is 99.9%. So that is the distribution table, and obviously I'm not expecting you to remember this. It would be virtually impossible to remember this. On the exam, you'll have access to this. You can also look up the Z table on various types of different calculators. So if you don't have this chart, obviously you'd need a calculator that would be able to give you that information. Now, sometimes you may be asked, for example, to find the area under a standard normal curve. When I say an area under a standard normal curve, I mean this curve, but you're asked to find, let's say, for example, what are the odds, in other words, what's the percentage of curve under 1.0, just to give you an example, under 1.0 standard deviations above the mean, which means everything from here on. Now, in this chart, we could simply count it. We could say, well, it's 50% less than 0. It has to be by definition. Plus 19.1 plus 15, which gets us 84.1. So under one standard deviation would be 84.1% of the entire graph, because you have 50 plus 19.1, which is 69.1, plus 15, which is 84.1. Or, if you wanted to look it up on the chart, and which you'll have to do if you don't have such a clear number as 1, you can go over here, and let's go to Z is 1, like as we looked at, 1 standard deviation above the mean, and look at that, 84.8413, okay, I rounded it off to 84.1, which is approximately 84.13%. So if I tell you that, let's say, find everything under the normal distribution curve, let's say to the left of Z equals 0.53, just 0.53, well, let's see. Okay, Z is 0.53. Okay, let's go here, because again, 0.53, and the answer would be 70.19%, or 0.7019. If I ask you what's to the left of 2.78, well, then I'd have to go down here, 2.7, and go all the way to 8 over here, which would be 0.9973, or 99.73%. If I ask you to the right of the distribution curve, which means to this side, to the big side of the distribution curve, well, then you'd have to do 1 minus that number. If I ask you, for example, what's to the right of 1.0, well, we know to the left of 1.0 is 0.8413. So to the right must be whatever's left over to get to 1. So it's 1 minus this number. Now 1 minus 0.8413 is, of course, 0.1587. And you could do it with a calculator, or you could do it in your head. So if you're asked to the left of Z equals whatever, then you just take this chart, whatever number is on this chart, 2.43 would be over here, etc. If it's to the right, it would be 1 minus that number. Unfortunately, the normal distribution curve, the z-curve, as we saw, only works when you have a fairly large sample size. And that's this idea about the nature of the universe, where randomly generated variables fall, really only applies when you're talking about large sample sizes, when you're talking about significant sample sizes. When you have too few sample sizes, you can't really use the z-chart, as it really won't be accurate enough. And when that happens, when you have less than 30 sample sizes, and 30 is again a fairly arbitrary number, but that's the one that is generally accepted for this purpose. If you have more than 30 sample sizes, you can use the z-chart. You can use the normal distribution. Generally speaking, if you're asked if you have 40 samples or 50 samples, use the normal distribution chart. If you have 30 or less, or 30 or fewer, you need to use a different chart, and that's called the t-distribution. The t-distribution is used instead of a normal curve when you're talking about a small sample size. You can always also use the t-distribution chart when you don't know the standard deviation, but again, we're not really going to worry about that so much in this course. We're really going to look at situations in which you know the standard deviation, of the sample that you're taking, but you don't know the standard deviation of the entire population. That's, as we move forward, that's the situation that we're going to be discussing. So for our purposes, you could assume that if the sample size is small, which means less than 30, then you're going to use the t-distribution model, whereas if the sample size is greater than 30, or 30 or greater, then you can use the normal distribution chart, which we saw a little while ago. That's this one. Now, the t-distribution curve, as you can see, is a little bit different than the normal standard deviation distribution. This, if you look at the light blue curve, this one that goes up here, that's the normal curve. That's the normal distribution curve. And you can see that is much higher towards the middle, whereas most of those results are going to be really, really close to the mean, in this box up here. That's why it's really high bump in the middle, because most of your results are going to be close to the mean. The lower the sample size, on the other hand, the less likely they're going to be closer to the mean. So for example, a t-distribution that is fairly close to 30 is still going to be somewhat close to the normal curve, but even then it's just going to have fatter tails. It's going to spread out much more slowly. You're going to have fewer right next to the mean and more examples that are further and further away from the mean. That's this pink line that is a t-distribution curve that is close to 30. So you're going to have a distribution curve that is similar to the normal distribution curve, but not quite as high in the middle. On the other hand, when you have t-distributions where the n is lower than 30, is less than that, where you have something like sample sizes of 10 or 15, what you're going to have is you're just going to have a much lower bump in the middle. The bell is going to be much less sharp. The results near the mean are not going to be as high. So the idea is the more sample, this is true with anything. This is true whether you're talking about political samples or any kind of study that you're doing for statistics. The more sample size you get, the better. Because the higher the sample size you get, the more likely that your results are going to be closer to the mean. Whereas if you have fewer sample sizes, you're going to have a very fat curve in the bottom, which means that you're going to have relatively few samples near the mean, and samples are kind of going to be spread out all over the place. Where the more sample size you have, like the dark pink and the blue, more results are going to be closer to the mean in the middle over here. What I have over here on this chart is the confidence chart, just like it's similar to this chart where we had with the z-table, the normal distribution table, except this chart, the one on the right side, applies to the t-distribution table. So in other words, this is what you're going to use when you have a sample size that is 30 or smaller. When you have 30 or 31 or bigger, you're going to use the normal distribution table, and when you have less than 30, you're going to use this distribution table. Now, what this distribution table means, it's similar to the other one, but it has another factor. The one on the left side is your quote-unquote degrees of freedom. Now, degrees of freedom is a very similar concept to the number of samples, but the way you figure out is simply n minus 1, the number of samples minus 1. So if you survey 21 people, for example, your degrees of freedom is 20. The reason why that is, long story short, is that only the first one is not variable. The first one is the one that, I guess, establishes the initial rule, and everything else then comes afterwards. But again, it doesn't really matter if you understand that. The key is to remember that the degrees of freedom is going to be n minus 1, the number minus 1. Remember, we also used n minus 1 for the denominator when we were figuring out the standard deviation in the previous section. So this chart is going to be used to figure out your TC. T stands for the t-distribution, and C for your confidence level. So TC is your confidence level based on the t-distribution table. Also, you notice there are two different possibilities on top over here. You have a one-sided diagram or a two-sided diagram, and that's very similar to the one that we saw before. Remember, the normal distribution table was actually a one-sided diagram or a one-sided chart, and in order to convert it, you had to double the difference between 1 and that number, as we saw in the last section. But just to reiterate, the difference between a one-sided diagram and a two-sided diagram is if you're looking for everything, let's say, to the left of one standard deviation away from the mean, you mean this entire area. That would be a one-sided. Two-sided is if you're looking in either direction. For example, if I say what percentage is going to be within one standard deviation of the mean either direction, well then it's two-sided. You're looking at just the stuff in the middle, and you're excluding what's over here, and you're excluding what's over there. So whether you're looking for a two-sided or a one-sided diagram, or excuse me, a one-sided or a two-sided confidence interval or chart, is going to determine which number you use up here. And what this means in English is that you take the percentage of confidence that you're looking for. Do you want to be 90% confident of your result? Do you want to be 80% confident of your result? Usually we're going to use this two-sided one over here because most times you're looking to determine whether something is accurate. It's possible for it to be off in either direction. Sometimes, on the other hand, for example, if you say, I want to see what the chances are that it's going to be no higher than 50 degrees today. Well, then, if you were looking, then it would be one-sided because you don't care how low it is. It could be 40 or 30 or 20 below or 100 below. That makes no difference to you. The only thing that makes a difference is that it is no higher than 50 degrees. So that's one-sided. On the other hand, if I tell you, well, the average temperature today is 50, and I want to know what the odds of it being within 10 degrees either way, up to 60 or down to 40. Well, that's two-sided, and that you'd have to look at as a two-sided diagram. And if you notice, the two-sided ones are always double the amount away from a 1. If you take 1 minus the one-sided and double it, you're going to get this. You're going to get the two-sided number. For example, the one-sided over here is 90%, and the two-sided is 80%, because if you have a 10% margin of error on one side, well then that same 10% margin on the second, if you do the same thing on the second side, it's naturally going to be double that amount. So you use one-sided when you only care one direction, and two-sided when you're looking for something in both directions. Usually, as I mentioned before, we're going to use the two-sided approach, but again, you'd have to look at the question carefully to determine which one you're going to use. Okay, and so you look at what you want in terms of your confidence interval. You then go ahead and look at your n-1, your degrees of freedom, and you determine how many standard deviations away from the mean you have to be. Let's take an example. Find the critical value TC for the given confidence level C and the sample size n. And we give you C is 0.70 and n is 22. Well, okay. If we're going to look at 70 here, so we'll look at, again, the two-sided. Unless you hear otherwise, you could assume that it's a two-sided issue. So we're going to look at 70. Then we're going to go down to n-1. Now, n was 22, so we're going to go to n-1, which is 21. And 70 and 21, you can see the value right over here is 1.063, which is, of course, our answer. And what this means in English is that with a sample size of 22, you can be 70% confident that the real mean is within 1.063 standard deviations from your calculated mean. You did 22 experiments. To give my day, let's say my 50-degree day example. If I went back over and I looked through 22 random temperatures on today's date, which happens to be March 14th. Again, that's neither here nor there. But if I said 22 random years, the mean temperature was 50 degrees, and so whatever. Let's say I figured out the standard deviation to be 10 degrees. Let's say, just for argument's sake, 50 degrees with a standard deviation of 10. So that means there's a 70% chance, based on my 22 samples, there's a 70% chance that today's temperature is actually, or the real mean, the real average, is going to be within 1.063 standard deviations of the mean that I figured out. Again, I took 22 samples. My samples had an average of 50 degrees and a standard deviation of 10. Now 10 degrees, that's 10.63 degrees because it's 10 times this amount. So that means there's a 70% chance, I can be 70% confident that the real average temperature for this date is within 10.63 degrees of this amount. If I wanted a higher confidence, if I wanted a 95% confidence, and I had the same number of sample size, well then I'd go to the 95, and then I'd go down to 21 again, and this is 2.08. That means that's over 2 standard deviations, which is a much broader range. Obviously, I want to be more confident, so I can't be as precise unless I do more experiments. If I go up to 30 experiments, well then all of a sudden, as you scroll down a little bit over here, the number of standard deviations increases. Decreases. Not by very much, but by a little bit. So our 1063 in 22 samples, and at a 70% confidence interval, if I did 8 more experiments to get my n-1 up to 29, that would go down to 1.055 standard deviations. Because the more experiments you do, the more precise a result you're going to get. And then once you go past 30, then you would turn around and use this table, use the z table, which is really going to give you the same basic idea, the same basic results. Okay, now we're really starting to get into the meat of the course. And we're going to start now with our kind of introduction to confidence intervals and of statistical analyses and when they're legitimate, how legitimate they are, etc. And before we do that, we have to learn about the null and alternative hypothesis. But even before we do that, we need to briefly discuss what a complement of a statement is. A complement of a statement is the opposite of the statement, to the point where one statement and the other statement combined have to have a complete probability of 1. To give you an example, it's raining and it's not raining are complements of each other. One of them has to be true. It either is raining or it's not raining. So the two statements are complements of each other, and so the complement of probability of A is probability of not A. There are other types of complements that are possible, but that's the most common scenario. The complement of I am speaking on the telephone is I am not speaking on the telephone. That's always the way it works. And the reason why it's relevant is because of this idea of the distinction between the null and alternative hypotheses. First of all, the null and alternative hypotheses are always complements of each other. In other words, the null and alternative hypotheses are statements, assertions, where one of them, by definition, has to be true. And if one is true, then the other is inherently not true. The null hypothesis, whenever you're talking about a statement that you don't know for certain whether it's true or not, and that's what statistical analyses are all about, the null hypothesis, which is referred to as H0, H for hypotheses, and 0, the first one, the initial one, refers to the assumed position or the default position. So, for example, if I tell you that it's sunny outside, well then the default position, the assumed position, my asserted position is that it's sunny outside. The alternative hypothesis refers, the HA, for alternative hypothesis, refers to the other position that is not the null hypothesis. And the best way, the most clear way, and perhaps the only way to prove that your hypothesis is correct, to prove your H0 is correct, is to refute the alternative hypothesis. You don't necessarily need to prove that your statement is correct, but you can prove that the null hypothesis, you can prove that the other possibility is incorrect. So for example, if I say it's sunny outside, and the alternative hypothesis, of course, is that it's not sunny outside. So if I can somehow prove to you, through a statistical analysis, that it is not sunny, that will essentially have the same impact of proving that it is sunny. So you can prove a null hypothesis by disproving the alternative hypothesis. And the HO and HA, namely the null and alternative hypotheses, have to be complements of each other, and they have to add adding their probabilities has to give you a sum of 1. If, for example, there's a 60% chance that any given day is going to be sunny, well then by definition, there's a 40% chance that the day will not be sunny. Let's take an example, a very simple example, then we'll look at more complex examples a little later. I claim that the mean exam average, the mu over here, is 75. My claim that the exam average is 75, that's the null hypothesis. That's the H0. That's my claim. That's the default position that we're going to be looking at. The mean not being 75, mean not equal to 75, is the alternative hypothesis, and that's what you need to disprove in order to prove your hypothesis. So for example, if we use the charts, if we use the experiments, and we use either the t-distribution table or the z-distribution table, depending on our sample size, and we prove to a 95% certainty that the mean not being 75 is not true, then we can say that we have established to a 95% certainty that our mean is 75. So let's take a look at some word-based examples. A tire company guarantees that its mean tire will last at least 5 years without blowing out. So what is our claim? What is our null hypothesis? And that is that the mean is greater than or equal to 5. 5, of course, being years. It will last at least 5 years, which means it's greater than or equal to 5. So what's our alternative hypothesis? What's the other possibility? The other possibility is that it's less than 5 years. Because if it's less than 5 years, then my null hypothesis is false. If it's not less than 5 years, then by definition that means that my null hypothesis is true. And there are two different types of errors that could be made when you're making an assertion of a hypothesis. One possibility is a false positive, and the other possibility is a false negative. A type 1 error is when I reject a null hypothesis that really was true. In other words, I say that I cannot prove H0. I say that I cannot prove my null hypothesis, when in fact I really could prove it. What are some examples of a false positive? A test that shows a patient has a disease, when in fact the patient does not have the disease. My null hypothesis that the patient did have the disease, in fact, was true. I'm sorry, I said that incorrectly. The null hypothesis in this case, the standard, the default would be, if you're testing a patient, anytime you're testing a patient for the disease, the null hypothesis is that the patient doesn't have the disease, because the patient's has always been healthy. A patient walks in, you don't automatically assume the patient has an ingrown toenail or bronchitis or a tumor or whatever it is. So the null hypothesis is, of course, that it's true that the patient is disease-free. If you get the alternative hypothesis that the patient has a particular disease, well, that of course would be the HA. So if the test shows my patient to have a disease when in fact the patient does not have a disease, that's of course an example of a false positive. A fire alarm going off when it indicates a fire, when in fact there is no fire. An experiment indicating a medical treatment should cure a disease, when in fact it does not. The opposite case is a failure to reject a false null hypothesis. Our null hypothesis was false, and nevertheless we did not reject it. A false negative. A blood test that does not detect a disease when the disease was actually there. A fire breaks out and the alarm doesn't ring. A clinical trial of medical treatment that does not show that the treatment works when really it does. Failing to show that the treatment works when, of course, it really does. So again, you can think of it, since it gets a little convoluted in terms of how it works, just think of it as a false positive or a false negative. If you think that you've proven a statement and it really hasn't been proven, that's a false positive. If you think you haven't proven a statement and you really have, that is a false negative. Okay, so here are some examples over here. A tire company guarantees that its mean tire will last at least 5 years, as we discussed before. The null hypothesis, which is the claim, is that the mean is greater than 5. The alternative hypothesis, the HA, is where the mean is less than 5. An example of a type 1 error, in other words, a false positive, is that where the actual mean of the tire is 6 years, which is true, which means our statement was really correct, and yet we rejected the null hypothesis. And the opposite is when the actual mean tire is 4 years, which means that our original statement was actually false, but I do not reject the alternative hypothesis. Here I do reject something when it should not have been rejected, so it's a false positive. And here I don't reject it when I should have, and so it's a false negative. Again, not a critical point in this course, but just one thing that could be relevant. Now, this is something that we discussed before already, but it's also important to understand the distinction between a one-tailed test and a two-tailed test. A one-tailed test is when you're looking for everything on one side, but you don't care about the other, whereas a two-tailed test is when you're looking for something within a specific range. To remember the example before, I ask you, what are the odds that it is going to be less than 60 degrees out today? Well, I don't care if it's what the temperature on the lower end is. I only care what the temperature on the other end is, on the higher end. And therefore, it is a one-tailed test. There's only one. This would actually be a right-tailed test. If you're testing whether something is greater than a particular number. In my example, my temperature example, let's say my null hypothesis is that it's going to be 60 degrees or less today. So when we do experiments, what are we looking for? We're looking for the possibility that it would be more than 60 because we're looking for the alternative hypothesis. Again, the null hypothesis, in my example, 60 degrees or less. The alternative hypothesis is over 60 degrees, 60.1 degrees or more. That would be a right-tailed hypothesis. We don't care about the lower end, which is all green, which is all fine. What we care about is the higher end, which is red. If it's the opposite, if I say what are the odds that it is going to be less than 20 degrees today, well, my null hypothesis, the assumption that's going in, is that it will be 20 degrees or higher, and it is disproven only if the alternative hypothesis, that it's 20 degrees or less, is proven. That's a left-tailed hypothesis because, again, we're looking for the possibility of something that is lower. Left and right are just two variations of the exact same thing. Left and right-tailed hypotheses are examples of experiments where we are only specifically looking for one side. We don't care about the other side. A two-tailed hypothesis, which is what most statistical analyses are, as we discussed before, is when you're looking to see if something is in a range, usually within one standard deviation or two standard deviations based on the z-chart or the t-chart that we looked at before. So in this example, we want, let's say, something to be we want to know if it's going to be within 10 degrees of the normal average. The normal average today is 50 degrees, let's say, and so we're looking to see whether it's going to be between 40 and 60. It's two-tailed because something below 40 is going to be in the bad area, the red, and something above 60 is going to be in the bad area, the red. So this is an example of a two-tailed hypothesis. Okay, so in an example of the greater than side, if my null hypothesis claims that the effect is no greater than x, so that would be a right-tailed hypothesis because we're looking for a value that is greater than whatever x happens to be. The opposite, of course, would be a left-tailed hypothesis. But if you're testing both, then it's two-tailed. If I claim that my null hypothesis is no greater than x and no less than x, well, then we're looking for that range in the middle near the mean, and it is a two-tailed hypothesis. Now we're starting to look at the most complex part of the course, and that is the issue of confidence interval. First, a little bit of background. Confidence interval is a way to express what level of confidence you're making an assertion with. For example, if based on the numbers I say, well, it's probably going to rain tomorrow, or President Obama is probably going to win re-election, or the Red Sox are probably going to win the game tomorrow against Pittsburgh or whatever. Anything that I say, assuming obviously I have some sort of mathematical basis, in and of itself it doesn't mean anything, because what does probably mean? Does probably mean 51%, or does probability mean 75%, or does it mean 99.999%? Obviously you want a higher level of confidence to what you're saying. Unless you know all of the data in the entire population, it's not possible to be 100% confident of anything. For example, I can tell you how many degrees it was yesterday in Los Angeles, California by going to weather.com and looking it up. But I can't, if I don't have every data point, if I don't have the data, if I'm looking for the weather in all different places and I do not have access to all that information, I may have to estimate it, and the question is, with how much confidence can I estimate it? And the chart that we looked at before, the t distribution, and more so the z distribution, the normal distribution table, was, obviously very much related to this, because we're talking about if we're looking for the average. Really, when people poll before elections to see who's going to win, what they're looking for is the average. They're looking for, well, 52% of the people are going to vote for candidate X, and 48% of the people are going to vote for candidate Y. Now, obviously, the problem is that unless they sample every single person, it's not possible to know for sure what the mean is. Just because you sampled 1,000 people and 520 of them said I'm going to vote for X and 480 of them said I'm going to vote for Y, doesn't necessarily mean that that's true for the rest of the million people who live in the state, or the million people who live in the district, or whatever it is. So the question really becomes, what level of confidence can you make your assertion with? Are you 90% sure that your numbers line up with the general population? Are you 95% sure? Typically, when you talk about things like elections, they usually talk about 95% confidence intervals, and because of that, that's a number that we're going to see over and over again in our examples, but there's no ironclad rule that says that it has to be 95, or it could be, when you're talking about, for example, whether a drug has a dangerous side effect, instead of relying on something like 95%, maybe you want to be 99.9% sure that it's going to be harmless before you actually use it. So statistical analyses are critical in so many different areas of our lives in terms of testing, polling, things like that, but it's also just as critical to understand what the results mean and to what level of confidence they are good, to what level of confidence they are valid. Okay. So first we're going to look for confidence intervals regarding deviations from one mean. In other words, how far away could something be from a particular average? Before we even look at this, let me give you an example. If I have a sample and I have, 10,000 people are going to take a test, and I give it to 100 people at random, and I want to try to test what is the population likely to get. What are the 10,000 people going to average? What do I think the 10,000 people are going to average? Well, in order to do that, number one, what I need to do is I need to figure out the mean. Then I need to figure out the standard deviation from the mean of the 100 people who actually took it. And then I could use the confidence interval charts and methods that we're going to see a little bit later on to determine how confident am I that the real mean, or the population mean, is somewhat close to our mean, to the observed mean. The population mean is the average of everybody that is going to take it. If 10,000 people are going to take it, what is the average of the 10,000 people going to be? Well, I only have data points from 100 people. So I don't know the population mean, but I can estimate the population mean, and I can estimate it to a certain degree of confidence. Maybe, for example, I can say that I am 95% confident that the exam scores are the exam mean for the full population is going to be between 82 and 88. That's the sort of thing that we're looking at when it comes to confidence intervals, and we're talking about deviation from one mean. Now, the reason I say one mean as opposed to two different comparisons, difference of two means, is because when we're comparing two fluid numbers, in other words, two numbers that you're not sure about, then it becomes a little more complex. An example of using two numbers is if I ask you, well, okay, 100 people took test A and got this, and 100 people took test B and got that, how confident am I that test A is really harder than test B? Now there you have two numbers, and you have to figure out the two standard deviations in two different sets, and that becomes a little more complex. But at the beginning, we're going to look for deviation from one mean. In other words, we're only looking at the mean for test A, our observed mean of the 100 people that took it, as opposed to the population mean, which is going to be the mean of all of the 10,000 people that take it later on. Okay, so how do you figure out these confidence intervals? We're going to look at examples, but let me tell you the steps first. First, you have to find the standard deviation of the population mean. I'm sorry, that's a mistake. You have to find the population of the sample mean. You don't know the standard deviation of the population mean because... I'm sorry, check that. I'm confusing myself. Let me start over. Okay, first you find the probable, the thing that threw me off over here is the probable deviation, standard deviation of the population mean. Remember, the population mean in general is the mean of the entire population, not just the sample size that you're looking at. So the way you estimate the standard deviation of the population mean is taking the sample mean, or the sample standard deviation, excuse me, by the square root of the sample size. So what does that mean in English? Let's say I have 100 sample tests, as we saw before, and I'm going to use a whiteboard here. So we've got 100 sample tests. Okay, so 100 sample exams. And we figure out that of the 100, now this is not the population mean yet, because this is just the sample mean. The population mean is the mean what all 10,000 takers would get, which we're really just trying to estimate because we can't prove until we have all 10,000 people take it. Okay, so our mean, let's say, is going to be 84. Now, now we need to take this and first figure out our standard deviation. Now you can figure out the standard deviation if you're given all the results and do it by hand or do it with Excel, but let's say for argument's sake that we're given the standard deviation. The standard deviation of the mean, of this particular mean, is 5, let's say. So the standard deviation of the mean of our sample tests and the standard deviation is 5. The way you figure out the entire population mean, in other words, the population standard deviation, excuse me, the standard deviation of the whole thing, our sigma of the entire amount, our sigma of the population, we'll write that over here, is you take the first standard deviation, the standard deviation of your sample, and divide it by the square root of the sample size. So in our case, our standard deviation was 5. Our sample size was 100. So I'm going to say the square root of 100. Now the square root of 100 is 10. It's plus or minus 10, but for statistical purposes you can ignore the negative value. So it's really equals 5 divided by 10, and your answer is 0.5, which means your standard deviation of the sample mean is 0.5. So let's put that number in the back of our mind now. Notice, of course, that the higher your sample size, the smaller this number is going to be, the smaller the population standard deviation is going to be. If this, for example, would be 1 instead of 100, so it would be 5 divided by 1, and your sample would be, your standard deviation would be 5, which would be a very high standard deviation. The higher the sample size, the smaller the standard deviation is going to be, which means your results are going to be more precise. Your results are going to be more accurate because your standard deviation, in other words, how far they spread out from the mean, is going to be much smaller. That's why whenever you're doing a bunch of tests, you want to try to do as many tests as possible. You want to get as big a sample size as possible in order to make your results more narrow and more focused, and therefore more reliable. The next step is to figure out the confidence interval that you are looking for. So in our example, let's say we're looking for 95% certainty. Well, how do we find how many standard deviations are going to allow us 95% certainty? Well, we can look at the normal distribution table because we have more than 30 samples. Remember, if we had less than 30 samples, we'd have to look at the t-distribution table. We have more than 30 samples because we have 100 in our case, so we're going to look at the standard deviation for the z-table. Now remember, the z-table is one-tailed, so you're going to have to double the distance from 1 in order to get the actual number of standard deviations. We want a 95% confidence interval, so we're going to have to use the z-table's 97.5%. Because the z-table is only in one direction, whereas, of course, we're looking for our result to be good in both directions. Our mean to look at how far away it would be in both directions. So in this table, we're going to look for the 97.5% confidence here, the 97.5% probability. And here's 97.4. Oh, there it is, 97.50. 0.9750, which is 97.5, and you can see this is 196. Okay, so 1.9, and then another 0.6 over here. So that's 1.96 standard deviations away. In order to get a confidence interval on the z-table of 95% altogether, we need our result to be within 1.96 standard deviations away. Once we figure out, we multiply the population standard deviation, which we had as 0.5 before, by the number of standard deviations allowed by our confidence interval, and then we can see, okay, that means that based on our case, moving back here, so based on our case, remember our population standard deviation was 0.5. Our confidence interval level, let me use a different color to distinguish. Our confidence interval, our confidence interval level would be at 1.96. We're looking for 95%, so a 95% confidence interval would be within 1.96 standard deviations. So we would multiply 1.96, which is the number of standard deviations we can be away and still be 95% confident, times 0.5, which gets you 0.98, which means that we could be, if this is a real-life scenario where we took 100 people and the standard deviation was 5, we figured out the standard deviation, and we had we could estimate that there is a 95% chance that the real mean of all the people that are ever going to take this exam, assuming they're randomly distributed, would be within 0.98 of the 84. In other words, it would be at 84.98 at the high, and at the low would be 83.02. It would be the mean for the population mean. I'm going to write this on the bottom. The population mean, the mean of the entire people, is going to be 84 plus or minus 0.98. And this, of course, is certain to a 95% confidence interval. In the next section, let's look at another example. Okay, let's look at an example. Let's take an example from scratch and we'll do the whole thing. The National Dairy Farmers Association says that the average price for a gallon of milk is no higher than $3.89. A survey of 50 random supermarkets around the country shows a mean of $3.74 and a standard deviation of 40 cents. At alpha, which means the confidence interval, that's that little Greek letter over there, is 0.05, which is the same thing as saying 95% confidence interval. An alpha of 0.05 means you can disprove it by proving that there's a 5% chance of the opposite. So it's the same thing as a 95% confidence interval. It's important to remember that, by the way. Is there enough evidence to support the association's claim? Okay. First of all, we can use the normal distribution table, which we will in a few minutes, since the number of samples is greater than 30. If it was less than 30, we'd have to use the t-distribution table. What are the hypotheses? Well, the assertion is that a gallon of milk is no higher than 389. So the null hypothesis, in other words, the asserted hypothesis, the default position is that the mean, the mu, or the mean, is less than less than or equal to $3.89, and that means that the alternative hypothesis, the one that we have to disprove, is that the mean is greater than $3.89. Okay, so let us go ahead and see how we would do this. And I'm going to do this over here on this little chalkboard here. All right, so what do we have? We've got a sample over here, and we have what do we have as our sample statistics? Our sample statistics. Our mean, and I'm just going to write the mean because I'm not really good at writing the mu, the Greek letter. Our mean was 374. Remember, this is the sample. We don't worry about so far the assertion. At the end, we'll see whether the assertion was made or not. But we're going to start off the mean. What is the standard deviation? Well, the standard deviation was 40 cents. So we're going to do 0.40. Because this is in dollars, so this ought to be in dollars as well. Is there enough evidence to support the association's claim? All right, so our first stage is to figure out our estimated standard deviation for the whole population. How do we figure that out? Remember, the sigma, the standard deviation for the whole population, is going to be the sample standard deviation divided by the square root of the sample size. So you take the population, the sample standard deviation, divided by the square root of the sample size. Now the sample size was 50. It said in the examples that you took a survey of 50 random supermarkets, so the sample size is 50. So then we could do this by hand, or we could do it on a calculator. I'll do it on a little calculator over here. And so I'll say the standard deviation, which was 0.4, and we will divide that. This is just a calculator emulator, by the way. And obviously, one of the things you need to be able to do is to operate a calculator, but this is relatively easy. You can download this, incidentally, if you want a calculator on your computer. You can just Google calculator emulator, and there's really lots to choose from. So we'll say divided by, and then we will open up parentheses because we're going to divide by the square root of 50. So I'll say 50, and then I'll do the square root, and this is a shift, so I'll push this to operate the shift, and then push the square root of 7.07, close the parentheses, and that equals 0.057. Of course, we could have done it the other way too. We could have done it something like this. We could have said the square root, the square root of 50 is 7.07. And it's more than that, but we're going to round it off to 7.07. And then we could have said 0.4 divided by 7.07, which is also obviously the same result, 0.057. Okay, so so now we've got 0.057. So our sigma, in other words, our population standard deviation, is 0.057. Now in this case that means 5.7 cents. Remember, this was in cents. 0.40 meant 40 cents, so this means 5.7 cents. That's our standard deviation. That's our population standard deviation. Now we have to go find out what our confidence interval is. Okay, well, what did we say we wanted? Back to our example. We wanted the alpha to be 0.05, which means a standard deviation of 95%. And so we're going to look on the normal distribution curve. We have more than 30 sample sizes. We have more than 30 samples. So we're going to look at the normal distribution table. Now remember, is this a one-tailed or a two-tailed distribution that we're looking at? I'm going to show this to you again, and you can pause it if you like, and before you figure it out. So now that I would pause it, and think to yourself, is this a one-tailed or a two-tailed? Okay, now that you've unpaused it, the answer, of course, is that it's one-tailed because you're only looking in one direction. The sample it says that the average price for a gallon of milk is no higher than $3.89. Well, you don't care how low it is. It could be $1, it could be 92 cents, it could be negative $1. I mean, for all we care, it makes no difference how low it is. It only matters that it's not higher than $3.89. So we're only looking for a confidence in one direction, which means we have a one-tailed distribution and one-tailed determination here, and so we're going to be able to use the z-table as it is. Remember, the z-table is also one-tailed. It's a one-tailed hypothesis, one-tailed distribution. So if we needed a two-tailed, we'd have to double the distance between 1 and that number, but here we can simply find what's going to give us 95%. What's going to give us 95% certainty? So I'm looking for the 0.95, and I see it's right over here. I see it's 0.9495 is over here, and 0.9505 is over here, and we'll use the one with the bigger error, just to make sure. And that comes out to 1.6. It's on the 1.6 line, and it's under the 0.5. That's this over here, so we'll call it 1.65 standard deviations. So in order to get a 95% confidence interval, since it's a one-tailed hypothesis distribution, 95% CI means that it has to be within 1.65 standard deviations. Fine. So what is our standard deviation? We're looking at our population mean standard deviation, which is 0.057 times 1.65. And we could do this in our head, or we can just do it on the calculator over here. Let's see. Here's the calculator. Let's clear it. And we'll say 0.057 times 1.65, that's the number of standard deviations, and we've got 0.094. So let's write that down over here. 0.094. And 0.094, of course, is the same thing as saying 9.4 cents. So what does this mean? This means that we can be 95% certain, since that's what the confidence interval we looked up, that the real mean, the real average milk price, is within 9.4 cents of our established mean, of our tested mean. What was our tested mean? 3.74, which means the lowest it can be would be down to $3.74. So if we subtracted 9.4 cents, we'd get 364.6. And if we added 9.4 cents, we'd get 383.4. You just had to add, obviously, the number of cents to the mean over here. And so the highest it can go, if we looked at it that way, if we looked at the highest within the 95% range, the highest end of the range, which is, since we're looking for the highest possible, the highest end of the range is $3.74 plus 9.4 cents, which is 3.83.4. Sorry, it's so small. Let me write it up here again. The highest is 383.4 cents. $3.83, really 383.4 cents, which is the same thing as saying $3.83 and 0.4 cents. Now, so if we go back to our problem, Well, what was the assertion? What was the null hypothesis? The null hypothesis is that it was less than or equal to 389. And that was the assertion, that it was no higher than 389. Can that be proven? Well, the answer to that is yes, because the highest it can be within the 95% margin of error, within the 95% confidence interval, the highest we came out that the real mean could be was $3.83.4, which is less than the assertion. So therefore, we can say that the assertion is correct. To break it down with a slide, again, you can review this later. That's why I gave you this slide, so you can work it out by yourself. A 95% confidence interval, the real mean has to be within 1.65 standard deviations, and of course that's because it's one-tailed. The error is only on one side, the error is only on the high side, so we just use the z-table to determine the 1.65 standard deviations from the 95% confidence interval. Our standard deviation is 40 cents, and to convert that from our sample to the population mean, we have to divide by the square root of the sample size. The square root of 50 was 7.07. We figured, again, rounded, but it's close enough. 40 cents divided by 7.07 was 0.057, 5.7 cents. 1.6, that's the standard deviation of the population mean. 1.65 of those was 99.4 cents, which means that we can be 95% confident that the real mean is less than 9.4 cents above or below the sample mean. And since the sample mean is more than 9.4 cents below the asserted mean, the HO, 389, we can be 95% confident, more than 95% confident, that the real mean is less than 389, and therefore we can accept the null hypothesis that the real mean, the mean over here, is less than or equal to $3.89. Well, that worked well when we had one mean that we were diverging from. In other words, the whole example that we looked at a moment ago in the previous section was all about trying to determine what your confidence is that a particular value is within a particular distance from one particular mean. Well, now we're going to move over to the situation where you're making a comparison. You're looking at two means that are kind of fluid. You have two objects and you want to know which one is more. You want to know which one is less. You want to know whether one of them is a certain amount more than the other one. Anything to that effect where you don't know for sure either mean. You're able to test each sample. You're able to test each and get a sample mean, but you don't know what the population mean is, and so therefore you're trying to compare two means at once. Well, the way to do that, and this is one of the few times in this course that unfortunately you're just going to have to memorize a formula. Fortunately, this is not a particularly complex formula. If you're comparing two means, the first thing you need to do is calculate the difference between the means. That's very easy. You figure out the mean of one, figure out the mean of the other, and then you just subtract. If your mean exam score for test number 1 is 85, and your mean exam score for test number 2 is 82, well then obviously your difference is 3. The standard deviation between the two is a little bit more complex. And to figure out the standard deviation between the two means, in other words, between the two quantities, between your two samples, you have to apply a formula. And the formula is this over here, the standard deviation of x minus y, in other words, the standard deviation of the difference. We're calling one of the quantities x, the other quantity y. There's no inherent rule why you have to do it that way, but of course that's what we're doing just for convenience. So the sigma, in other words, the standard deviation of the difference between x and y, which is x minus y, equals the square root of the standard deviation of x divided by the sample size of x plus the standard deviation of y divided by the sample size of y. Sometimes you'll see this called s to the second plus, or s1 squared plus s2 squared instead of sigma, but it's the same idea. What you're looking for is the standard deviation of one quantity divided by its sample size plus the standard deviation of the other quantity divided by its sample size, and then take the square root of the whole thing, and there you have your standard deviation of the difference. You have your standard deviation of the distinction between your two samples. Once you have that, as we'll see, it's pretty much the same thing as doing the previous example. It's pretty much doing the same thing as looking for the standard deviation from one mean. So once you do that, you just continue as we looked at before. First, you have to find your confidence interval. Now, one thing that's important to first determine, of course, whether this is a two-tailed distribution or a one-tailed distribution. Now, before, in our previous example, we looked at a one-tailed distribution because we were talking about a maximum, right? Well, in our case, if you're looking at the difference between two means, in other words, if you're looking at which one is higher than the other, by definition it's going to be two-tailed because by definition it's going to depend on both directions. If you're looking to see is one too far apart from the other, well, being too far above and being too far below are both going to be problems, or both going to mean that they're separated by a statistically significant amount. So whenever you have a distance of two means issue, you're probably going to have a two-tailed distribution, as we do, and so therefore, when you're finding the confidence interval and you're using the z-table, you need to calculate, 95% for a 90% confidence interval, 97.5 for a 95%, as we discussed before. Then once you have the standard deviation and your confidence interval, remember your standard deviation you figured out using this formula, square root of each standard deviation divided by its sample size. Then you do the same thing as you did in the previous example. You multiply the combined standard deviation by the number of standard deviations required by your confidence interval, and then you see, is there a statistically significant difference? If the number you come up with is 5, and your confidence interval requires that they be 4 away, in other words, your standard deviation is 5 away and your confidence interval requires that they be 4 away, well then there's a significant difference between them. If so, in other words, if there's a greater difference between the two means, between really the two standard deviations, between the two means, if there's more of a difference than is required by your confidence interval, there is a statistically significant difference between them. If not, there's no statistically significant difference between them. This, of course, is the sort of analysis that's usually done when you're talking about political polls. If the question is whether enough voters are going to vote for the Democrat or the Republican, well, that is an issue of the difference of two means, and you would take the two standard deviations, apply whatever confidence interval you're looking for, and see if there is a statistically significant difference. Okay, so let's now look at an example and how we would go about figuring that out. Same basic idea as we did before, except here to figure out the difference in standard deviations, we are going to have to apply our formula. Let's look at this example. In a study, a researcher finds that the mean weight loss of 49 people on diet pill A after 30 weeks is 17 pounds with a standard deviation of 7. The mean weight loss of 75 people on diet pill B after 30 weeks is 19 pounds with a standard deviation of 5. At a confidence interval of 5%, is there enough evidence for the researcher to conclude that B is more effective than A? Well, if you look right away, it seems that B is more effective than A. B lost the people 19 pounds, same sample size, same number of months. Whereas A lost the people 17 pounds, which is less. So at first, it looks like B is a better pill, assuming that, of course, the experiment was done in a scientific manner. But the question we have to ask ourselves is this a statistically significant difference? Could the difference between 17 and 19 have been a product of luck or random chance? Or does this indicate to a 90% degree of certainty that in fact B is a better pill than A? So let's look ahead and determine how we would go about doing this. Okay, so let's do this problem. I'm going to write in the little corner up here the vitals over here. We had diet pill A and we had diet pill B. And let me make this a little thicker so it's easier to read. We had 17 pounds was the mean, and we had a standard deviation of, let's see, standard deviation of 7. And for B, we had 19 mean and a standard deviation of 5. Okay, so let's apply the formula to figure out the difference, the standard deviation of the difference between them, of B minus A or A minus B. It makes no difference which way you put it. Okay, so remember, it's the square root of the first sigma squared, we'll use S, it's a little bit easier, divided by the sample size for A, so we'll call it A sample size. And for the second one, we will use the same thing, sample size 2, which is for B, divided by the sample size for B. Now back to the question, you can look back at the last section if you like, or in the PowerPoints. The sample size, for A we had 49, and for B we had 75. So let's go ahead and figure this out. So we've got the first one, the standard deviation 1 was 7. Remember, for A was 7 squared, divided by the sample size, which was 49, plus the standard deviation for B, which was 5 squared, divided by the sample size for B, which was 75. So if we're going to look at the sigma, we've got 49 divided by 49 plus 25 divided by 75. Now, of course, 49 divided by 49 is 1. And 75 divided by 25 is 1/3. So our sigma, the difference, the standard deviation of the difference between the two quantities, is the square root of 1 plus 1/3. Now 1 plus 1/3 is of course the same thing as 1.33333. And if you take the square root, you can do this on a calculator obviously. If we open up a calculator here and we say 1.333 whatever, and we click the square root, it comes out to 1.15. If we do it to another place, I think if we round it to another place, it comes out to 1.155. Of course, it keeps going on, but we'll round it to here. We'll round it to 1.155. This is the standard deviation of the distinction of the difference between quantity A and quantity B. And now we need to figure out our confidence interval. Now, getting back to the question, let me find the question over here. We wanted a confidence interval of 90%. Now remember, this is of course two-tailed, because an error in either direction is what we're looking for. We're looking for an error in either direction, not just greater than or less than a particular one. So because we're looking for a 90% confidence interval in either, so we really need a 95% on the z-table. The z-table assumes only a one-tailed, and so here we're going to have double the error. In other words, we're looking for double the error because we're looking for an error from either side. So instead of looking for 90%, we'll look at 95%. And as you can see over here, 95%, the first one that's over 95%, the 0.095, or 0.9505, excuse me, is 1.65 standard deviations. It might, by the way, it might even help to remember that, some of the famous ones. The 95% standard deviation is 1.65 deviations. I think the 97.5 we saw before, which was 1.96 standard deviations. But anyway, so we're talking about 1.65 standard deviations because we're looking for 95% confidence, which will give us 90% confidence in a two-tailed example. So we're looking at 1.65 standard deviations. So getting back to our example, we had figured the standard deviation of 1.155, and I'll delete the rest. Just keep the most important number over here, because that's the one that's important, 1.155. We'll use 1.155 times 1.65, And our answer is approximately 1.91. Obviously, it's a little off, but if we round it off to two places, we'll get about 1.91. Now, if you'll recall, the actual difference between the mean was 2. Remember, the mean of A was 17, and the mean of pill B, in terms of weight loss, was 19. So the difference between A and B, the mean of B minus A, was 2. And according to our statistical analysis, based on the standard deviation times the number of the confidence interval, we can be 90% confident that the two means should be, or would be, if there was no statistically significant difference between them, less than 1.91. Because, in fact, they are bigger than 1.91, they are 2 away, we can be 90% certain that there is a statistically significant difference between them. So, in other words, with a confidence interval of 90%, we can say, with 90% confidence, that pill B is in fact better than pill A. Because pure chance, pure luck, pure randomization would only count for a maximum difference of 1.91. It would not account for a 2-pound difference. And that's our answer. Now I'm going to take you through the answer that I put over here. Obviously, you can always review this on the slide. This, remember, was the distinction. We found the distinction between them. We just said this a little while ago. This was the standard deviation of quantity A. This was the standard deviation of quantity B. Eventually, we got 7 times 7, which is 49 over 49, plus 5 over 75, which was 1.33. And the square root of that got us a standard deviation of 1.55. We used the Z distribution chart, the normal distribution chart, to figure out that a 90% confidence interval requires us to be within 1.65 standard deviations. And the difference was 2, which is more than 1.91. Remember, our 1.155 standard deviation between the two means times 1.65 standard deviations was 1.91, but our difference was 2. Therefore, we can be more than 90% confident that pill B, is more effective than pill A. So if we go back to our original hypotheses, our null hypothesis was that the mean of B is bigger than the pill of A, so we can accept that to a 90% confidence interval. And the alternative hypothesis, that pill B was less than or equal to as effective as the mean of pill A, we can reject that alternative hypothesis. Hello, and now we're doing one supplemental section to this statistics video, and what I want to do now is the issue of binary distribution in polling. Earlier we discussed the issue of standard deviation, how you calculate standard deviation. Part of this is, of course, how you build out from standard deviation and establish confidence intervals. In the other parts of the video we discussed what happens if you have multiple possible results. If you have, for example, you have 100 exam takers, and some of them get a 72, and some get a 78, and some get an 84 and 83, and you figure out the standard deviation between them, and then you could build confidence intervals, and you can continue with all the statistical analyses. Well, I want to also discuss the case of a binary distribution, which is actually a lot simpler because there's a very, very basic and simple formula that you can use to establish the probabilities in the case of a binary distribution. Binary distribution means the issue of what happens when you only have two possible results. For example, if you're talking about a coin, there are only two possible results. There are heads and there is tails. There is no third possible result. When we talked about exams, we talked about there are many different possibilities because you could get an 83 and could get an 84 and could get an 82. So therefore there are many different examples, but if, for example, we would have only taken the exams that passed and the exams that failed, then it would have been much simpler because, again, there are only two possible results. Now, if we are talking about the probability, for example, of a coin flip, if we're going to solve it in numbers, and obviously everything you deal with in statistics you want to be able to convert it into numbers, you can't use a formula where heads is one, where you have heads and tails represented. So instead, what you need to do when you figure out a binary distribution is assign one possibility a possible value of 0, and the other possibility a possible value of 1. For example, if you're talking about two coins, or one coin with two possible sides, you could assign heads as a value of 0 and tails as a value of 1. Now, you could have done the opposite. You could have done tails as 0 and heads in 1, and that's fine. But the point is, either way you want to work it is fine, as long as you put one of them as 0 and the other as 1. If you want to talk about the mean of course being average, if you have a fair coin, which means that a coin, the average of all of the probability of any event is 1 plus the other, divided by the number of possible events. Remember, if we had the probability of getting an 85 and we had 3 results, and we had a 90 plus an 85 and an 80, well, the mean, the average, would be these 3 plus 3, and of course that would equal 85. Now, when you're talking about a binary distribution, one of them is 0 and one of them is 1. Now, of course, what's the probability when you flip a coin? The probability of getting heads is a half, right? Whenever you flip a coin, the probability is a half, which is 0.5, plus the probability of getting tails, which is also 0.5, divided by the total number of possibilities, which of course is 2, and 0.5 plus 0.5 is 1, plus divided by 2 is of course 0.5. Now, so I think it should be obvious and fairly intuitive to everybody that the odds when you're talking about a fair coin are even, and therefore you can establish it as 0.5. The average is halfway in between heads and tails, half the time heads and half the time tails. Now, when you're talking about the variance, based on this principle that we discussed way earlier in the course, the standard deviation is the weighted sum of the square differences, you can derive a fairly simple formula for the variance of a binomial distribution. I'm not going to prove it here, but just take my word for it. There are other videos in which you can actually prove it. But the variance, it can be derived by simply p times 1 minus p, where p equals the probability of 1, and so therefore, of course, 1 minus p is the same thing as probability of 0. So p, for example, would be the probability of a tails in this example, whereas 1 minus p would be the example of heads. Which means that the standard deviation, when you're talking about a binomial distribution, since the standard deviation is the square root of the variance, the standard deviation of a binomial formula is the square root of p times 1 minus p. Okay, so now we have established that when you're talking about a binary distribution, and again, binary distribution simply means a distribution where there are only two possibilities altogether, is the square root of p times 1 minus p, with p being one possible result and 1 minus p being the other possible result. Now, typically, p is going to be the maximum of 1, which means 1 minus p will be the inverse number. If p is going to be 0.6, then 1 minus p is going to be 0.4. Now, hopefully the reason for this is obvious, because if there are only two possibilities, then the two possibilities have to add up to 1. For example, when you're flipping a coin, the possibility of heads is 0.5, which is p, and the possibility of tails is also 0.5, which is, of course, 1 minus p. Now, they happen to be the same, which 0.5 is the same thing as 1 minus 0.5. To illustrate this, let us take a look at an example. Now, building a confidence interval and establishing how confident you are in a particular series of results is the same whether you're talking about a binary distribution or a non-binary distribution. The only difference is how to figure out the standard deviation. Normally, you have to use that whole complex formula when you're talking about finding the standard deviation, but when you're talking about a binary distribution, you can use this shortcut, where the standard deviation is the difference between, is the square root of p times 1 minus p. Now, as an example, let's take something that was similar. It was something that I'm borrowing from the recent election. I'm recording this video in November of 2016, where the presidential election between Donald Trump and Hillary Clinton just happened. And one of the big stories about the election was an upset in the state of Michigan, where Hillary Clinton was favored. In the Real Clear Politics final average, Clinton was up by 3.6%, and she ended up losing the state. And I want to discuss that, how big an upset was that, statistically speaking. Now, of course, the catch or the problem with any poll is that the poll has to be scientifically accurate and scientifically legitimate. And if the sample that you're surveying is not random for whatever reason, whether they're your fault or not, you're not calling enough cell phones, you're not calling, people aren't, certain demographics aren't home as much, those are going to be problems with every polls, and those are the sorts of things that polls have to make sure to try to figure out how to work around. But let's assume, for argument's sake, that the polls that put Clinton up 3.6 points were 100% accurate, and so I'm going to give you an example, and we're going to use the central limit theorem and this rule over here to kind of figure out how big an upset that would be. So we've got a problem here. In a survey of 900 likely Michigan voters before the 2016 election, 466 say they will vote for Trump, and 434, for Clinton, and 434 say they will vote for Trump. Assuming the survey is scientifically legitimate, always a dubious assumption, but let's see if we can make that assumption here. How confident can we be that Clinton will win the state? Now, of course, this percentage, as I mentioned before a moment ago, was Clinton approximately 51.8% and Trump approximately 48.2%. And again, I picked those numbers because they have a 3.6 point spread, which was the Real Clear Politics final average between the two states. Okay, so let us take a look over here at how we would go about doing that. Now remember, based on the central limit theorem, you need to first figure out the population standard deviation. And the population standard deviation was the standard deviation divided by the square root of the sample size, in this case n. Now, of course, in our case, the sample size is 900 because the problem tells you that there were 900 likely voters. Okay, now the sample size, because it's the standard deviation, because it is a binary distribution, is going to be this formula. So we're going to have the square root of p times 1 minus p, and then to get the population standard deviation, we're going to take the square root of the sample size. So let's plug in our numbers over here. Of course, our p, now we can use p as the chance that Clinton's going to win, and 1 minus p, the chance that Trump is going to win, or vice versa. It makes no difference. It's going to be the exact same thing. So for our purposes, we're going to call p the Clinton win, and we'll call 1 minus p the chance, obviously, the chance of a Clinton win, and 1 minus p we'll call the chance of a Trump win. So our p is 51.8%, or 0.518, times 1 minus p, 1 minus 51.8, which is obviously 0.482. And we will divide it by the square root of n, which is the square root of 900. Okay, let's pop out our calculator over here. Okay, so let us do this. We've got 0.518 times, sorry, I'm just using a different calculator here. Okay, 0.518 times 0.482. So we get a little under 0.25. We get about 2.4968. Let's take the square root of that. The square root of this number, which of course is this number times this, which we get as 0.499, so right about 0.5. So let's call this equals, we can round it off to 0.5 divided by the square root of 900, which is 30. So let us take this number and we'll divide it by 30.
and we are going to get approximately 0.0166, which I'm going to round off to 0.017. So I think you can call this 0.017, which of course when you convert it into percentages is approximately 1.7%. So the population standard deviation of our sample size over here, at our sample, is approximately 1.7%. That's the standard deviation based on our 900 sample size, assuming a perfectly valid and a perfectly legitimate sampling. Now, once we do that, now we can look at, okay, how many standard deviations do we have to be off? Now, our survey had Clinton up 3.6%. So if we want to know how confident we can be, let's see how many standard deviations we can be off without Clinton losing it. And of course that means 3.6, which is what our survey said, divided by 1.7 to see the number of standard deviations. Now 3.6 divided by 1.7, I'll do this off screen, I think you can all figure this out pretty much, divided by 1.7, excuse me, is 2.12. I'll round it off to approximately 2.12, which means Clinton is up 2.12 standard deviations based on our sample size. And if you look at the z-table, let's go find the z-table over here. Here we go. Here is the z-table. We're going to look at the number, for our number of standard deviations, 2.12, which is about 0.174, which is about 0.0174, excuse me, about 1.74%, which means only about 1.74% is to the right of this z over here, because we're 2.7 standard deviations away. Now, by the way, remember, this is a one-tailed hypothesis, because we don't care if the survey is up in Clinton's direction. We only care if it's down, or towards Trump's direction. So the margin of error in this case is at 2.2 standard deviations, we are really over 98% confident. There's only really over here actually, 1.7%, which means that based on this, we could actually be 98.3% confident that Clinton is actually up. Now you might say, well, okay, well then obviously that didn't work, because if we were 98.3% confident and yet it lost, well, that's because unfortunately, polling is not perfect. Polling has problems, and that's why polling in general is not 100% accurate, and it's never going to be 100% accurate. But if it were perfect, and somebody was up by based on a sample survey of 900, and somebody was up 3.6%, that means they would have over a 98% chance of winning. So that's basically how to take binary distributions and to use kind of the same things as we discussed in previous videos to establish confidence intervals.
I want to next look at something called a regression equation, or a regression analysis. Now, first of all, a regression analysis is very complex, much more complex than what we've been discussing so far, and fortunately it's a little bit beyond the scope of the course. I'm not going to actually teach you how to do regression analyses. If you're interested in learning on how to do regression analyses, which can be very interesting and very useful, you can go to Khan Academy, or you can go elsewhere online and you can learn how to do them. The only thing that we're going to be discussing in this course is how you apply a regression equation, which is really extremely easy. Getting the regression equation is the hard part. The easy part is actually applying it. And that's because once you have the regression equation and you have the data that make up the variables in the equation, all you have to do is just substitute. A regression equation defines the relationship between various relevant factors. Calculating the equation is hard, but once you have it, applying it is very easy. Let's take a look at an example. An equation that can be used to predict fuel economy in miles per gallon of automobiles is y hat, which is really an estimate of y. We don't know exactly what y is in a regression equation, so it's used with that little hat on top, which means it's an estimate, equals 34.5 minus 0.003 x1 minus 0.005 x2, where x1 is the engine displacement, and x2 is the vehicle weight. In other words, you don't really have to understand all the nuances of this. What this means is this is a way just to predict fuel economy based on certain random parts, and you're given x1, the value for x1, and you're given the value for x2, and you are asked, using the equation, predict the y value for the given values of the independent variables. And the reason why this is extremely easy is because all you have to do is substitute the x1 over here for the x1 in this equation, and the x2 for the x2 in this equation in order to figure out what y is. And we're going to quickly look at how to do this. And so let's go ahead. Let's just substitute. I mean, this is really extremely easy. Y, or y hat, again, because it's an estimate, equals 34.5 minus 0.003 times x1, and x1 was 305, just substituting this value for this variable, minus 0.0056 times x2, which was 3750. Again, just substituting this for this. And to figure this out, we could do it by hand, but it's easier just to do it with a calculator. So I am going to clear this, and I'll say, well, what did we have? 0.003 times 305 equals 0.92. So I'm going to put a 0.92 over here. And then we had, let's clear this, let's 0.0056 times 3750, and that gives us 21. Minus 21. This value, of course, stays the same, the 34.5. And, well, 34.5 minus 21 is 13.5. And so 13.5 minus 0.92 should be 12.58, I believe. And you can do that in a calculator also, but it was relatively easy to do in our heads. And that's our answer. Our y hat, our estimated miles per gallon, according to this particular regression equation, was 12.5 miles per gallon. And the last type of statistical analysis we're going to do in this course is the chi-squared test, sometimes also called the chi-squared test. Now, first of all, what chi is, it's a Greek letter also, and it looks similar to an X with a little flourish in the upper left-hand side. So sometimes if you see something that looks like an x squared, in statistics it really means a chi-squared. Now, a chi-squared test is similar to a statistical analysis for a confidence interval that we discussed before, but a chi-squared test is what you use when you have a bunch of data points and you want to see how well they fit a particular prediction. And the only way to really discuss this and really learn it is to do an example. So a chi-square test is used to tell you how good a fit your statistic is relative to an observed pattern of data. Let's take an example, and we're going to follow this example all the way through to the end. I posit, in other words I assert, my null hypothesis, my HO, is that a golf course's yearly customer base, about 20% come in July, 20% come in August, 15% come in June, 15% in September, 12% come in May, 10% in October, and 8% the rest of the year, for November through April. So my null hypothesis is that this is the breakdown of my customer base. Again, we can't use what we discussed before in terms of a two-tailed or a one-tailed test, because we're not looking for one particular median. We're looking for a whole bunch of data points, and we want to know how close all of these data points are to the actual reality. So this being our null hypothesis, the chi-square calculates the likelihood of getting a result that lies within the range of our observed data. So we'll take, in a minute we're going to take an example of results that we would get, and then we're going to go back and make a determination of how close our hypothesis, or whether our null hypothesis was proven to be correct within a certain confidence interval. But again, you see what the difference between this and what we discussed before is that here we're looking for a whole bunch of different data points, whereas before we were looking for is your mean within the mean of the within the population mean. So let's take a look at an example. I measure the following numbers with regard to my golf course example. I measure that 43 in a particular year, 43 come in July, 38 come in August, 35 in June, 28 in September, 31 in May, 16 in October, and 9 in November through April, for a total of 200 customers. So our question is, this was our original assertion, this was our original null hypothesis, that in any given year, this will be the likely distribution, about 20% each in the summer months, and obviously the further away from you get from the summer, the fewer customers. And the question is this data consistent with this null hypothesis? That's what the chi-square is designed to measure. So the question is, can I reject the claim based on this data that the predicted data is not correct, assuming a 5% confidence interval, which is really, it's a 5% alpha, which is really the same thing as 95% on the other side, obviously. In other words, is there at least a 5% chance that the predicted data is an accurate reflection of the random distribution, or the alternative would be there's a 95% chance that it is not. So, let us take, first thing you need to do is figure out what the predicted data was, and then determine whether that is actually consistent, or how far away with your original prediction. I'm sorry, take the prediction originally, and then take what actually turned out, and see how close they are for each individual component of it. Let's take a look at this middle chart over here, which really just synopsizes what we just saw in the previous two slides. November through April, our original prediction was 8%, if you recall from this. And how many did we actually got? We actually got 9. Out of 200 people total, 8% would be 16. That would be the predicted. 8% of 200 would be 16. But we only actually got 9. In May, our prediction was 12%. And, well, 12% of the 200 customers would be 24 of them. How many did we actually got? We actually got 31. So in other words, what this chart does is it just goes through each set. And this is a good way to, you don't have to draw a chart like this, but this really helps you break down the problem. And for each one, we have, really these two columns are the ones we're really going to use over here, because this shows you the difference from the expected value. The expected value, based on your prediction, would be in this column, and the actual value would be in this column. You can see in May it's more than the predicted value, in June it's more, July more, August less, September less, October less. But that could just be random luck. The fact that your numbers are a little off doesn't mean that your original prediction was wrong. If your numbers are very off, then it's probably true that your original prediction was wrong. If your numbers are a little off, maybe not. And really the chi-square analysis is how we measure whether your data is too far away to establish your hypothesis. In other words, whether your hypothesis can be disproved from the data. Now we need to use the information that we just found in this, that we just used this little chart to generate. to figure out our chi-square statistic. Now, the chi-square statistics formula is really not that complex. It's the summation, which means the addition of all of the data points, their difference from the expected value squared, divided by the difference from the expected value squared divided by whatever the expected value is, and plus etc. here means you have to do each one. That's really what a summation means. This little thing over here means just a whole bunch of things added to each other. In other words, the difference from the expected value squared divided by the expected value of this one, then the difference from the expected value squared divided by the expected value of this one, etc., 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 until you finish all 7 of them over here. So let's take this chart and let us actually calculate it out. Okay, let's rewrite the formula over here just to make sure. Our chi-squared formula, which looks something like this, is the summation. I'm not drawing that properly, but anyway, I don't really know how to draw it very well. Of each difference from the expected value squared divided by the expected value. So let's try each one individually. We'll put the chi-square over here, equals, and we'll try each one individually. So let's take November through April. Now, November through April, the predicted was 16 and the actual was 9. So that's 7 squared, because it's 7, the 16 minus 9 is 7, obviously, divided by the expected value, which was 16. And we'll have to do the second one again. The second one was the actual was 31 and the predicted was 24. So again, the difference is 7. So we'll do 7 squared divided by the actual value, which is, by the predicted value, which is 24. The third one, we've got June, which is the predicted is 30, the actual is 35. So we can do 35 minus 5, which is of course 5 squared, divided by 30. You can do this all in a calculator, by the way, in one step or Excel or something like that, but we'll do it out just to try to illustrate how it's done over here. The fourth one is July, which is 43 minus 40, which of course is 3 squared, divided by the predicted value, which is 40, plus August, 40 minus 38, 2 squared, divided by the expected value, which also was 40. September, which was 30 minus 28, also 2 squared, divided by 30, which was the predicted value. And then we had October, which was, well, the difference between the predicted and actual was 4. So that's 4 squared divided by 20, because 20 was the predicted value. Okay, let's multiply this out. We'll say chi-square again equals 7 squared is 49 divided by 16, plus 49 divided by 24, plus 25 divided by 30, plus 9 divided by 40, plus 4 divided by 40, plus 4 divided by 30, plus 16 divided by 20. Okay, and for this we could do it by hand, but we'll do it on a calculator. I mean, there's really no reason to do something like this by hand. Let me try to make this a little small. Okay, I just rewrote them on the side because there was no way to get the calculator in with them written across the top. These were the 7 fractions that we just had, so let's do them one at a time. I'm going to use open parentheses for each one because we want to add them all together. So I'm going to open parentheses and say 49 divided by 16, close the parentheses, that's the first one, plus, and again open the parentheses, 49 divided by 24, close the parentheses, that's the second term. Okay, third one, open parentheses, 25 divided by 30, close the parentheses. Then add the fourth one, which was 9 divided by 40, open parentheses, 9 divided by 40, close the parentheses. Then the fifth one, add open parentheses, 4 divided by 40, which we know is going to be 0.1, of course. Okay, and then add the fifth parentheses, which was 4 divided by 30. 4 divided by 30. Okay, and then finally the last one, I'm just going to add, I know that 16 over 20 is 0.8. It's the same thing as 4/5, so we're just going to add 0.8, and we have our answer as 7.20. I think it's actually a little bit, this is rounding off a little bit. I figured it out on the slides. I figured it out to be 7.196, but that's close enough. If you're rounding it off to two places, 7.196 would round off to 7.20. So our answer would be 7.2, 7.196, something to that effect. That is our chi-square statistic. You can see that in the next slide over here. Same thing we just did. 16 minus 9 squared divided by 16, 31 minus 24 squared divided by 24, all the same thing. The difference between these two columns squared divided by this column, the predicted value. So our chi-square statistic is 7.196 or 7.2. And the next thing we need to do is we need to use another chart. Now we've already looked at two charts, the normal distribution chart, that's the z chart, and the t-distribution chart. Well, now we've got a third chart, and that is the chi-square distribution chart. And again, you're also going to have access to this, but these things also appear on many types of calculators. And in order to make a determination of significance in a difference between statistics, you can use the chi-square chart and kind of a grid in terms of how far away your numbers can be from the accepted ones. So we have over here, what did we want originally? I think we wanted a 5% alpha, right? We want a 5% alpha, and of course a 5% alpha is right over here, 0.05. How many degrees of freedom? Well, degrees of freedom is always n minus 1, the number minus 1. Here, how many statistics were there? There were 7, I believe. 1, 2, 3, 4, 5, 6, 7. So our degrees of freedom are 6. So if we look in degrees of freedom, and we go across to 5%, the alpha of 5%, we get 12.59. Whereas our actual value, our actual chi-square test was about 7.2. And so therefore, we cannot reject the initial claim. We cannot reject the initial claim to a 95% certainty. There's more than a 5% chance that the initial distribution was true. Based on a 95% certainty level, in other words, it's possible that the variance we had from the actual golf customers, from the ones we predicted originally, could have been a consequence of luck, could have been a consequence of random distribution. Our chi-square statistic was 7.196. On this chart, based on an alpha of 5%, we could have had a distribution as high as we could have had a chi-square statistic as high as 12.59. The greater the chi-square statistic, the more off your numbers are. Our numbers weren't off enough, so therefore we cannot reject the original claim. It's possible that the original claim is true. Note that if our alpha had been 50%, let's say, well, then we could have rejected it. If our alpha was 50%, then our chi-square number would have had to have been less than 5.35 in order to avoid rejecting it. That's why the level of confidence that you're looking at has to be told to you. There's no way you would inherently know that offhand. You have to be told in the problem what your alpha is. If you ask me, are these numbers, based on these numbers, are these numbers incorrect? Can we state that these numbers are incorrect? I would have to answer you, well, it depends what level of certainty you're looking for. Do we want a 95% certainty that the numbers are incorrect? Then no, we can't say that. Do we want an 80% certainty? Can't say that either. We can say with 50% certainty that the numbers are incorrect, but not any higher than that, because the chi-square statistic was 7.2 approximately. And that's how you use chi-square statistics to determine certainty of whether the numbers you actually garnered from a series of statistics match the actual numbers.